Now, today, speaking of which, we are going to be learning about the law of conservation of mass. The law of conservation of mass. This is going to be the second major driving principle of grade 10 chemistry. What was that first one? Why do atoms form bonds? Why do atoms form bonds? That was the entire purpose of everything we've learned so far.
Yeah, full shells.
To get a full shell of outer electrons, because then they are stable and happy, right? So atoms form bonds to get a full shell of outer electrons. Second half of chemistry, we're going to be focused on this, the law of conservation of mass. This is going to allow us to build those recipes of chemistry. So what is the law of conservation of mass? Well, it states that in a chemical reaction, I'm just going to abbreviate reaction like that from this point forward. Mass, we'll say matter here. Change the definition. Matter, aka mass, cannot be created or destroyed. In a chemical reaction, matter, aka mass, cannot be created or destroyed. Now, this is not to say we can't destroy matter, but we get into that realm, we're entering the realm of like nuclear physics, right? So, for our purposes, when we are doing chemical reactions, matter cannot be created or destroyed. So what does that mean in a practical sense, though? So if I had some amount of reactants and they made some products, what do you think remains constant? What do you think remains constant? So what does this mean for practical purposes? This means that the mass of the reactants will be the same as the mass of the products, right? So your mass will not change. Now, in saying that, for our purposes, that's still not the practical definition. What do you think is going to happen in terms of the number and type of atoms? Do you think the number and type of atoms will be the same in the reactants and the products? I see some heads kind of nodding. Yes? Yes. So for our purposes, the main way we are going to look at the law of conservation of mass is that the number and type of atoms in the reactants will be the same as the products. So our matter is conserved from reactants to products, right? If we had 10 hydrogens and 5 oxygens in your products, you will have 10 hydrogens and 5 oxygens. Now, when we take this and we start to apply this theory to chemical equations, we end up with a skill called balancing. Right? So what this is really saying is that your chemical equation must be balanced, right? You need the same number and type of atoms in both your reactants and your products. So the same number and type of atoms in your reactants and your products. Now, let's look at an example. Let's say you have, let's keep it simple. We'll say, for example, hydrogen gas reacts with oxygen gas to form water. So, very simple example. Hydrogen gas reacts with oxygen gas to form water. Now, I kind of lied to you yesterday when I said that you're writing down your word equation and your chemical equation. Actually, what you wrote down was your skeleton equation, your unbalanced chemical equation. So, first up, I want you to write down your skeleton equation, which is really simply just your unbalanced chemical equation. So that's really the skill you learned yesterday. All right, so your unbalanced chemical equation. And what is that going to be? Someone want to take a stab at it? Yes?
H2 plus O2 equals H2O.
Excellent. I love that you said H2 and O2. Why is it not H and O? Why is it not H and O? Why is this wrong? H plus O gives you H2O. Why is that wrong? Yep. Oh, you guys are good. They are diatomic, right? So these are the elements, remember those Hofbrinkel elements? If you forget to pair these up, you are going to be losing a lot of marks because a hydrogen by itself and oxygen by itself, that's a fundamentally different ingredient than H2 and O2. So remember, you cannot forget about those Hofbrinkel elements. Now we're going to be using that other skill that we practiced just a couple of days ago from grade 9. Counting atoms. Counting atoms. So once you have your skeleton equation, we're going to put a set of steps here for balancing. So let's put here, balancing. So we're going to say step 1. Write down your skeleton equation. And then step 2 is count atoms. Put a little more specific here. Count atoms in reactants and products. So we did step 1, we wrote down our skeleton equation. Step 2, we need to count the atoms. So what separates our reactants from our products again? Yeah, the arrow, right? So this here separates our reactants from our products. If we look on this side, how many hydrogens do we have? How many? I heard it 2. Yeah, there we go. We have 2 hydrogens. How many oxygens do we have? We have 2 again. How many hydrogens do we have on this side? 2. And how many oxygens? 1. So after you count atoms in reactants and products, and we'll say, and and determine what's not balanced, what's unbalanced. And in this case, what is unbalanced? Oxygen, excellent, right? We have 2 on this side and 1 on this side. So currently, our recipe doesn't follow the law of conservation of mass, right? We have a different number of atoms on one side versus the other. And again, in chemistry, we will never create or destroy matter. So you can never have a different number on either side. Now, how do you think I'm going to balance it then? Do you think it's right to put just like a 2 right here? Would that balance it out? Oh, you guys are very good today. Why would that be wrong if I did that? Does anybody know what this is? You may have put it on your cut when you were a kid, bubbled up.
Peroxide?
Yeah, that's hydrogen peroxide. So, by adding that 2, we fundamentally change what it is, right? H2O is, well, you need that every day to survive. If you drank pure H2O2, that would not end well for you. So H2O2 has, it's called oxygen radical. It's very reactive, which is why it can kill bacteria, but it also kills your skin, right? It's actually recommended you don't use peroxide anymore. It'll take a little bit longer for your wounds to heal, believe it or not, because it does kill a lot of your own cells as well. So fundamentally, these are different things, right? By adding a 2 there, we changed what our product was, right? We originally were baking a cake, and now we have a bottle of Lysol under the sink, right? So they're fundamentally different things. So we can't do that. We can't do that, right? We can't just put a 2 there. What can we do? What do you think? Sorry? We're not going to be changing our compounds at all. We're not going to be using Lewis-Carroll multiple here. So let's say we're making a cake, right? And we're trying to produce a cake, but our recipe isn't right, right? We have the wrong ratio of flours and eggs. So what could we do? We could change, for example, how many cups of flour we use in our recipe. We could change the number of eggs we use in our recipe. We can't change our ingredients, but we can change how much of each ingredient we use, and as a result, how much product we get. So the reason I had you count atoms by using those little coefficients in front was because that's how we're going to balance chemical equations. So step 3, and this is the only way you can balance, by the way, you're going to add a coefficient to balance add a coefficient to balance, and then repeat step 2. So every time we add a coefficient, we're going to recount our atoms. This is an essential step. We're going to recount, and then we're going to ask ourselves, is anything still unbalanced? If the answer is yes, then we got to go to step 3 and add another coefficient to balance it out. So again, we are trying to make our recipe for chemistry that abides by the laws of nature, that follows the law of conservation of mass, where the number and type of atoms on this side is equal to this side. So right here, our number of oxygens is not balanced. How can we make it so that it balances with that side? What coefficient could we put in front? And remember, coefficients tell you how much of that molecule or formula unit or atom you have, or element you have. Yeah, you're right. What is it?
2.
Yeah, you're right. If we put a 2 here, now we've changed how many atoms we have on the product side. How many hydrogens do we now have?
4,
We have 4. And how many oxygens do we now have?
2,
Yeah, we have 2, right? So now do our oxygens balance out? Yes, right? So is there anything that is unbalanced? Our hydrogens are unbalanced now, right? So how am I going to balance out my hydrogens? We're going to now do step 3 again, right? We're going to add another coefficient. How are we going to do that? You're right. We're going to add a 2. Where are we going to add a 2? Excellent. We're going to add a 2 in front of our hydrogen. When we recount now, how many hydrogens do we have? We have 4. So now we have a recipe that follows the laws of nature that makes sense, right? We have 2 cups of flour to 1 egg gives you 2 cakes. Clearly that'd make the worst cakes of all time, but you get the idea, right? So we're trying to come up with a recipe for our reaction. And we do that with balancing. Now, really, this is all there is to balancing, but there's a lot of tips I can give you that will help you, because it does get pretty complicated, to be honest. Let's look at a couple more examples here. Yeah, let's do that tip first. So let's say let's go back to butane. It's on my mind because the lighter's still sitting right here. Let's go back to butane. What is the chemical formula for butane? Do you guys remember? It's fine. C4H10. So butane reacts with oxygen gas, which is what? O2. And this is going to give you what? I'm just seeing if you guys remember from yesterday. It's going to give you fire, of course, but you're going to produce water and carbon dioxide as your 2 products. Whenever you burn any hydrocarbon or any fossil fuel, you're going to be producing CO2 and H2O. Now, this one here is a little trickier because there's a lot of things that are unbalanced. This leads into what I would call one of my important tips here. We're going to call this tip number 1. If there is an element by itself, and here I'm going to say by itself in quotation marks, because this is going to apply to your diatomic molecules as well, you're going to balance that last. You're going to balance that one last. Now, is there any element up here that's by itself? Yeah, oxygen is, right? Oxygen is. Why would you want to balance that last? Say that again, sorry?
You can do as many as you want.
Yeah, right? Because you can do as many as you want. So if it's by itself, no matter what number I put in front of oxygen, it's only going to change my number of oxygens. So if you have an element by itself, always balance it last, because by putting a coefficient in front of oxygen here, I'm not changing any of my other atoms. I'm just changing oxygen. So really important, balance it last. So let's do that. Let's go through this problem together and let's focus on doing oxygen last. What's step 1?
Write down skeleton equation.
Correct. Do I have the skeleton equation? I kind of skipped step 1, right? I already have the skeleton equation in the interest of time. What is step 2? Count. We need to count atoms. So how many carbons do I have on this side? We got 4 carbons. How many hydrogens? We got 10 hydrogens. And how many oxygens? We got 2 oxygens. Excellent. On this side, how many hydrogens do I have? How many carbons? 1. And how many oxygens? Ah, you guys are good today. Yeah, we have 1, 2, 3 oxygens. So if you have an element that's repeated in your reactants or your products, you have to count the total number, right? So there's 1, 2, 3. So what is unbalanced here?
Everything.
Literally everything, right? Everything's unbalanced. But what should we balance last? Oxygen. So it won't matter here which one you choose to balance first. So let's do, what do you feel like, carbon or hydrogen?
Hydrogen.
Oh, okay, let's do carbon. I heard two things. Let's do carbon. How are we going to balance out our carbons? How are we going to balance out our carbons? We have 4 on this side. We have 1 on this side. How do I make those numbers equal? Where am I going to put a 4? Excellent. I'm going to put a 4 right there. And after I add a coefficient, what do? I have to recount. I have to recount, right? Every time I add a coefficient, I'm going to recount. And this is just going to make it so that you won't make any mistakes as you go along. Because sometimes, by adding a coefficient in front of here, because we're changing 2 elements, it might balance things out. So we have now 4 carbons and how many oxygens? We definitely don't have 2. We don't have 8. We don't have 7.
We have 12.
We don't have 12. We have 4 times 2 is 8 plus 1 is 9. Okay, so what is unbalanced now? Oxygen and hydrogen. And we should do oxygen last, so let's now balance our hydrogens out. So we have 10 here, and we have 2 here. How do I balance that out?
The 5 from base 2.
Excellent. If we put a 5 here, 5 times 2 gives us 10 hydrogens. But how many oxygens do I have now? Not 14. We have 8 plus 5. Hey, there we go, 13. We have 13 oxygens, right? Oh, it's getting messy. Let's just do that. We have 13 oxygens. All right, so now is everything balanced out? No, it is not. It is not. What's not balanced? Oxygen. Oxygen is not balanced. Now, again, if it's by itself, we can balance it last by putting some number here. Now, which number will give us 13 oxygens? Bit of a trick question. Oh, excellent. 6.5. 6.5. Now, if I put 6.5 here, that will balance it out. Because what is 6.5 times 2? 13, right? So now everything balances. But, and this is a big but, can you have half of a molecule? No, right? You cannot have half of one of your ingredients. That's not the way chemistry works. You can't have just half of something, right? These are whole number ingredients. So this brings me on to my next tip. Tip number 2. You cannot have half a particle. And by the way, I haven't been using this word a lot, but that's my general word for formula unit, molecule, element. You can't have half a particle, half of one of your reactants or products. So again, this is my word for element, compound, formula, unit, molecule, the whole shebang. Therefore, if you get a 0.5, you must multiply all coefficients by 2. Because what is 2 times 0.5? It's 1, right? So if you ever get 0.5 as one of your coefficients, you cannot have half of a molecule of oxygen. That's not the way chemistry works. So now we have to multiply all of our coefficients by 2. So if I do that, if I multiply it all by 2, what do I get? So I'm going to take this whole thing, I'm going to multiply all of our coefficients by 2. I'm not multiplying our ingredients, I'm not changing our ingredients, just the numbers of our ingredients. The ratio will remain the same though. So when I do that, what do I get? How many butane molecules? Remember, if there's no number there, what are we assuming? It's a 1. So what's 1 times 2? 2. So we have 2 molecules of butane reacts with how many molecules of oxygen? 13 molecules of oxygen. And this will produce how many molecules of H2O? 10 molecules of H2O. And how many molecules of carbon dioxide? 8. Right? So now we have a recipe where all of the atoms are balanced out. Sometimes students will feel a little lost and they'll be like, Mr. Saul, I don't know if I did this right or wrong. What is a way you can check your answer? Think about that. How could you check your answer to know if you're right or wrong? What do we do in step 2? Count. You can always recount your atoms, right? If you recount your atoms and they balance on both sides, you know you did it right. So you can always double check your answer. Well, let's write that down as tip 3. Why not? You can always check to see if you did it correctly by recounting your atoms. Right? If they balance, you did it right. So very briefly, let's recount our atoms here. How many carbons do I have on this side? 8. How many carbons do I have on this side? 8. How many hydrogens do I have on this side? 20. How many do I have on this side? 20. How many oxygens do I have on this side? 26. And on this side I have 10 plus 16, which is 26. So we know we did the problem correctly. So that's tip number 3. Let's move on to a very important tip. And this tends to be one of the harder types of problems that students struggle with. I'm going to let you try this one on your own, and then you can see very quickly what the issue is. So let's say we had do you want to do that? Yeah. Okay, so based on what we learned, I want you to take a minute right now and I want you to try to balance this question. Alright, so I gave you a more or less impossible task there. It is extremely challenging unless you are really good at math, but there's a tip to make this really easy. And this is a really important tip to remember, which is why I just put you through that punishment. And the tip is this: if you have a polyatomic ion, if there is a polyatomic ion that is unchanged from reactants to products, treat as a single unit when balancing. Now, there's a reason why I put that kind of in quotations there. So if there's a polyatomic ion that is unchanged from reactants to products, treat as a single unit when balancing. Now, if we look at our chemical equation, well, the skeleton equation, does sulfate still exist as sulfate in your products? It does, right? You still have SO4 in your products. Does nitrate still exist as nitrate in your products? It does, right? So when you are balancing these things out, this trick is pretty important, otherwise you're going to kill yourself, because oxygen was repeated, which makes it super hard to balance just by counting atoms. But remember, in an ionic compound, what needs to balance? This is the reason why this trick works. What needs to balance? Not the number of atoms. In the chemical equation, the number of atoms needs to balance. I'm talking in an ionic compound, what balances out? The charge balances out. And that's why this little trick works. So if you have a polyatomic ion that remains unchanged, you can treat them as a single unit. So let's start here with irons. How many irons do we have? We have 2 irons. How many sulfates do we have? We have 3 sulfates. How many magnesiums? We have 1. And how many nitrates? We have 2. We go to our product side now. How many irons do we have? We have 1. How many sulfates? We have 1. How many nitrates? We have 3. And lastly, how many magnesiums? We have 1. So, what is unbalanced? What is unbalanced? Everything except for magnesium. Everything except for magnesium. Now, is there any element that's by itself? No, right? There isn't. So we're just going to pick one element and start balancing. I maybe should have added that to step 3. When you're balancing, just do 1 at a time, okay? 1 at a time and then recount. So let's balance out, I don't know, it doesn't matter really. Let's say iron. Why not? Let's balance out iron. How am I going to do that? I have 2 on this side, I have 1 on this side. Yep. 2 where? Excellent. Now, as I add a coefficient, I have to recount my atoms. So now I have 2 irons, but how many nitrates do I have? I have 6. Excellent, I have 6. Alright, let's balance out our nitrates. Why not? So I have 6 on this side. How do I get 6 on this side?
Put a 3 from the magnesium.
In front of the magnesium nitrate? Excellent. We put a 3 there. Now we have 6 nitrates. And we have 3 magnesiums. Now let's balance out our magnesiums. Why not? So we have 3 magnesiums here. How do I get 3 on that side? I put a 3 in front of here. So now I have 3 magnesiums and how many sulfates? 3. Okay, so am I done? Yes, I am done. How many sulfates do I have on this side? How many do I have on this side? 3. It all balances out. So I intentionally put you through the pain of trying to count atoms and not use this tip, hopefully in the vein that you actually remember this tip. Because without it, you are going to sit there and you are going to drive yourself insane on a quiz or a test, okay? So remember this tip, it is extremely important. So when you're balancing polyatomics, you need to treat them as a single unit if they remain unchanged. Now, let's go to tip number 5. I don't know how many tips I'm going to do today. These are all just off the top of my head. Tip number 5. Cool, this is a good one. So let's say I had a compound that looked like, this is a very simple example, but something that looks like this. Often students, when they try to balance this is kind of the thought process they'll go through. How many oxygens do I have on this side? We have 3, right? So we have 1 nitrogen, we have 3 oxygens, we have 1 nitrogen, we have 2 oxygens. Often students will look at this and be like, okay, so that means I need to put a 1.5 here. Okay, because if I put a 1.5 there, then I have 3 oxygens, right? But I got 1.5 nitrogens. I can't have a 0.5, so I need to multiply everything by 2. And then I get 2, 2, 3. And then, well, now I've got 3 nitrogens here, and I've got 2 nitrogens here, and then students just keep going down this path endlessly. They keep going down this path in circles and circles and circles, and their numbers keep getting bigger. Now there's a tip here. If you are spinning in circles, it's likely because you have an element that's repeated in either your reactants or your products. So tip number 5. If an element is repeated in your reactants or products, if an element is repeated in your reactants or products, and it's odd, right? If it's odd numbered, make it even. This will save you a lot of heartache. Make it even, okay? So, we have 1 nitrogen and we have 3 oxygens. Here we have 1 nitrogen and we have 2 oxygens. So we have oxygen repeated in our reactants, and it is an odd number. We have 3 of them. How can I turn that into an even number? Yep.
Can you put a 2 in front of
Not in front of the oxygen.
the nitrogen?
The nitrogen monoxide, right? We put a 2 in front of the nitrogen monoxide, and now when we recount, we have 2 nitrogens and we have 4 oxygens. So by making it even, you can see right away that this problem now is extremely easy to balance. What do we need to do to balance out our nitrogens or our oxygens on this side?
Put a 2 in front of it.
Yeah, if we put a 2 in front of it, well now we have 2 nitrogens and 4 oxygens. Does our problem balance out? It does. So again, if you ever have this situation where you find yourself going in circles where your coefficients keep getting bigger, that's one of the likely culprits because your element is repeated and it's easy to get into that cycle. Now, my other tip, the other reason you may get into that cycle, endless loop of coefficients keep going up, is because you started with the wrong recipe. So, actually, let's teach you this through an example. Let's say you had this. I want you to take a second right now and try to balance this, okay? Alright, so does anyone know why this is impossible to balance? You would have just been going in circles that entire time. This brings me on to tip number 6. Tip number 6. If the problem is impossible to balance, your skeleton equation is probably wrong. And that was the issue here. That was the issue. Sorry I put you through that. Again, you'll just go ad infinitum. You'll just keep going on forever and ever, cycling and looping through. So you need to stop yourself and realize, okay, there's something wrong here. And in this case, it's pretty subtle. Does anybody know which of my chemical formulas is wrong? Your iron, by the way, the charge on your multivalent metal is not going to change from your reactants to products. What was my charge on iron here? What was my charge on iron? No, there's a charge on it. What's the charge on sulfate? Remember for multivalence you need to work backwards through your anion. What is the charge on sulfate? Look it up. 2 minus, right? And if we have 1 sulfate that accepts 2 electrons, how many electrons must this iron have gotten rid of? 2. It would be 2 plus. That is the charge on this iron. What is the charge on nitrate? It's not 2. What is it? It's 1 negative. And our charge on our iron is not changing. It is still 2 plus, and that's 1 negative. Therefore, the correct chemical formula would have been that. So, such a small little tiny mistake, but that'll make it impossible to balance. So I can't stress enough how important it is that if you are still struggling with ionic bonding, with covalent bonding, you need to master that skill. Otherwise, you're going to get into situations where you really don't understand what you're doing wrong. You're going to keep cycling endlessly. And I see it all the time. Whenever I give out this chem unit test, I always get a unit test back where a student has scribbled so much on the page that they've almost like worn through the paper. And they're like at like 500 is their coefficient, right? So Really important. If it feels impossible to balance, you probably screwed up your recipe, right? Your skeleton equation is probably wrong. Sorry, that was super mean. But now it's actually quite easy to balance. Now it's quite easy to balance. So we have 1 sodium, 1 nitrate, 1 iron, 1 sulfate. Here we have 2 sodiums, we have 2 nitrates, we have 1 iron, and we have 1 sulfate. So this one's actually extremely easy to balance because, let's balance out our sodiums here. How do I get 2 sodiums on that side? Where? Right there? Yeah. So if I put a 2 here and we recount, we now have 2 sodiums and 2 nitrates. So we are balanced, right? So a very, very easy balancing problem was impossible with just a very, very small mistake. So keep that in mind. I think that's it for my tips, actually. Oh, I have one more tip, actually. Last tip, tip number 7. I swear the number of these tips changes every year. Tip number 7. Tip number 7 is, if you get into that situation where you can't balance it and you know your skeleton equation is right, restart. So if you can't balance, right, you've tried everything, you can't balance it out, restart the problem. Restart the problem, but start by balancing a different element or polyatomic ion first. Sometimes, if you don't balance the right element first, the problem becomes impossible. I can't think of a great example off the top of my head right now, but there are certain chemical equations where you're like, okay, I'm going to start by balancing sodium. And if you go that road, you'll end in one of those endless loops. So sometimes you just need to take a breath, restart, and start by balancing a different element first. Okay? That's my last tip.